Hello everyone, my name is Chenliang Chai from Tsinghua University. Then let me give a talk about the DB4AI overview, including the motivation, framework, and some fundamental techniques. So let's first talk about the challenges in machine learning. First, the machine learning models definitely need high-quality training data. However, it is always expensive to hire experts to acquire or label sufficient data. Second, a large number of training data naturally makes training less efficient. Besides, many typical model structures are becoming larger and deeper, especially for deep learning models. So this makes the machine learning pipeline more inefficient. Third, model training is not a one-shot process, and data scientists always train iteratively, test many models, and select the most appropriate one. But these trained models are hard to manage because they incorporate too much information. Hence, how to manage these models and the corresponding data artifacts remains a challenge. To address this challenge, both DB and machine learning communities propose an end-to-end data analysis pipeline, where many DB techniques can be utilized to benefit the effectiveness and efficiency of the machine learning tasks. We discuss relevant techniques from these three aspects along with the machine learning pipeline. First, the pre-ML, which is also named by data preparation, is needed for preparing high-quality training data, including data discovery, cleaning, and labeling. Secondly, model training consists of a number of time-consuming steps, including feature selection, model selection, as well as training and inference stages, which can be accelerated using DB techniques like materialization or parallelism. Thirdly, DB-based techniques can always be used to manage the trained models, including model storage, query, deployment, and debugging. Thus, the above steps have been extensively studied recently, and we review them thoroughly in this tutorial. We first talk about the data preparation. As reported by Forbes, data preparation accounts for about 80% of the work of the data scientist. Also, as discussed by Google, machine learning code is less than 5%, and other parts including the data collection, feature extraction, serving infrastructure, or monitoring. So let's first talk about the data discovery. Data discovery aims to retrieve training data related to the machine learning tasks from external resources like the web, data warehouse, or data lake, which is the first step in data preparation. However, in real scenarios, usually only a small number of data is available, lacking attributes, tuples, or features. To address this, many researchers have studied to discover more data for better model performance. In this part, we categorize the data discovery as attribute or tuple level and table level data discovery. The goals of data discovery are as follows. The first, items in a table should belong to a specific domain, so we may hope to discover as many items as possible in the domain. Second, we expect that the discovered entities or tables should be integrated into the table. That's about accuracy. Thirdly, most time there are a large number of data in external resources. The efficiency is another problem. The last one, most methods only consider fetch more related data without considering whether this data can improve the downstream model. So let's see the table about the comparisons of data discovery. The first column is the category, and the second column refers to that whether it can benefit the machine learning model or not. And the second column refers to the method. And the first column denotes which model the machine learning oriented method can benefit. And the source column refers to where we can discover the data. Then let's see how to discover new items or attributes. First, let's see the data-oriented method. We talk about discover from the surface web, discover from the hidden web, and discover from the humans. First, let's see the info gather. So suppose we have a query table, namely the base table. InfoGather leverages a vast corpus of HTML tables on the web to discover the missing cell by attributes or several examples. And it can also discover attributes by the cell values. The basic idea is to first identify the web tables that have matching schemas with the base one, but it always suffers from the low accuracy and coverage. So the InfoGather proposed a holistic probabilistic method that considers multi-hops relations of tables to conduct the value inference. Then let's discuss how to discover from the hidden web. The smart crawl aims to discover from hidden web by querying APIs like Yelp and DB4AI. For example, we want to discover the rating attribute of the restaurant by querying the Yelp, but the number of query is limited or the query is not free. So the optimization goal is to reduce cost, which is the number of the queries while discovering more complete items or attributes. For example, we can submit a very specific query like the Thai noodle house. So we can retrieve an accurate rating, but the number is always limited, say only one. We can also submit a general query like the type. In this way, we can acquire more, but some of them may be useless. So there is a trade-off. So let's see the pros and cons of the discovery from the web. The pros are that first, the automatic methods, they are automatic methods with high efficiency. And concretely, the surface web, it considers different HTMLs holistically with low cost, which can fill both tuple cell values and attributes. And the hidden web, always clean and accurate, where user-friendly APIs can be used. And the cons are as follows. These methods do not consider much semantic information, and long-tail cases are not easy to cover. For surface web, the data is always dirty, and for hidden web, the data is clean but costly. Then let's consider how to discover from the crowd. The crowd field aims to discover from the crowdsourcing, which provides user-friendly interface for works to collaborate on the web. For example, the worker can retrieve the fresh entities, the whole entity, or the missing cell values. And the workers can also vote for each other. So the crowd EC also aims to discover from the crowd, but the difference is that it has a more fine-grained optimization goal, including the quality, cost, and completeness. The quality means that we should discover items belonging to the domain. For example, if we want to collect the NBA players, and if one provides a soccer player, it is wrong. And also, we hope the workers to provide distinct entities, because if many workers provide duplicate entities, we should pay them, but it is wasteful. So there are two models. One is worker elimination, which eliminates low quality workers to improve the quality, and the other one is incentive pricing. We provide bonus to encourage workers to provide distinct entities to reduce the cost. And the pros and cons are listed as this. The pros are humans can provide semantic aware items, and they can check for each other with high quality. And the important one is that the long tail cases can be discovered more easily by the human intelligence. And the cons are the crowd workers have high latency, so it is not so efficient. And the crowd is not free, so they cost too much, but the cost control techniques can be applied. And the quality should be carefully controlled, including the distinctness. And then we talk about the machine learning oriented, which considers the downstream machine learning model performance. The above method just enrich data set without considering the performance improvement it follows. So this method, the auto-augment focuses on the image data rather than the tableau. So for image data, they have many augmentation operations like flip, rotate, scale are always applied to enrich the training data for performance improvement. Auto-augment uses reinforcement learning to search a sequence of optimal augmentation operations automatically. Specifically, each policy defines which operations to use and the probability of applying the operations in each batch. The agent first predicts a policy from the predefined search space. Then a child network is trained to achieve certain accuracy after applying the policy. Finally, the accuracy is regarded as a reward to update the prediction strategy in the first step. And the pros are the automatic and efficient discovery without human involved. And the second one is that the method cares about the machine learning performance in iterations. And the cons are just the auto-augment just discovers from the training set rather than involving real fresh data. And this method is limited to images but hard to structured data or text. Then next, we introduce the table-level method, which focuses on discovering tables based on the user requirement. So GOOD is a table-level method which manages the data in the data lake and provides an interface that allows users to explore the tables. Specifically, it stores information like a dataset schema, similarity, and provenience between datasets. Users can search and browse datasets using the keywords. However, such systems have limited usage in ML because they cannot support to search related datasets given a query dataset, which is a common requirement when current data is not enough. To this end, the algorithm is proposed to use a graph-based data structure to discover data. It provides flexible queries to query the dataset based on the user request, so that one can find candidate dataset to join. Based on the database meta information and a given ontology, algorithm matching the database and references using embedding methods based on which relationships between tables are established. Thus, highly related table can be found and the link can be propagated using the transitivity to find more tables. However, the above methods do not consider the downstream machine learning model. The pros of these methods are they provide user-friendly interface and users can query the desired tables easily. And they can manage the large number of heterogeneous datasets in the data lake. And we can also recommend more related tables besides the query table. And the disadvantage are that they just rely on the external reference to link related datasets, and they discover tables that only have similar semantic meaning without considering the machine learning performance. Then we come to the Helmet project. It answers the question that whether the foreign key joins between the base tables and tables in the data warehouse are necessary with the goal of improving the performance of the machine learning model. If not, some tables in the data lake can be proved in advance without drawing and training, so that the efficiency is improved. The basic idea is that the foreign key in the base table has been encoded enough information of candidate tables. For example, suppose that the base table is customer and one of the candidates is the employer, so they can be joined through the movie ID. So since many customers might see the same movie, so it is reasonable to use movie ID as a feature directly, rather than drawing the two tables. Specifically, Helmet proposed a measurement called the risk of representations, which is ROR, that leverages the VC dimension to compute the difference of the train and test errors of the machine learning model if the join is avoided. So the higher the ROI, the join will be more necessary. Otherwise, one may consider to drop the candidate table. However, this method is limited to models like naive Bayes and logic regression with VC dimension linear to the number of features. So ADA is another machine learning-oriented data augmentation framework that discovers tables from the data lake so as to improve the performance of the downstream machine learning model. Unlike the previous helmet, it supports fuzzy join with data from data lake. So one can conduct this using the brute force approach which is join the base table with all related tables and then conduct feature selection. But the join is always time consuming. We can improve the efficiency through two aspects. One is to reduce the size of this base table, and the other one is to join fewer tables. So ADA leverage these two ideas. So therefore, ADA samples some representation tuples using into simple heuristics from the base table when the base table size is large, and they utilize these samples to learn the augmentation plan. Then they conduct a step-by-step fuzzy join. It further improves the efficiency by joining the base table with the candidate table step-by-step rather than join all of them together. First, it sorts the candidate table based on their relevance to the base table. This can be done by the ORO. Then it joins the table step by step based on the ordering. In each step, the other feeds a batch of tables to join with the base table considering the trade-off between storage overhead and efficiency. And then they conduct feature selection, train the models, and test the accuracy. When the accuracy does not increase or a predefined budget of steps have been achieved, the augmentation process terminates. So the pros are it considering the model performance. The join tables can improve the model performance, and they support both PKFK and fuzzy joins. And some acceleration techniques are proposed, like sampling and join step by step. And the disadvantage are that the join is still time consuming because there still exists a large number of candidate tables. And the second is that the loss of missing values can appear because not all items can be joined. So here is the takeaway of data discovery. Data discovery enriches the tuples, attributes, or features of the dataset, aiming to improve the quality of the machine learning performance. But not all methods can directly improve the machine learning models. These methods just consider to enrich the dataset, discover more tuples, more attributes, or just the table can be unique or joined. They do not consider the machine learning performance. So besides the performance, the efficiency is another significant concern because there are always a lot of tuples or tables in the data lake that we can train. So we always use join, which is very inefficient. Then let's talk about the data cleaning. So the data retrieved from the external resources is always dirty. So data cleaning is always applied to detect and repair the dirty data. So the U.S. government reports that the dirty data results in a total loss of U.S. dollar about 600 billion a year. So there are many types of dirty data, including the inconsistency, duplicates, outlier, missing value, mislabels. So there are a lot of tutorials and surveys talking about the data cleaning, how to detect, where to detect, and what to detect dirty data. But in this tutorial, we focus on the problem that do we need to clean all types of dirty data for the machine learning? And the answer is no. So the motivations are that the different type of dirty data have different impacts on the machine learning models, and different data items also have different impacts on machine learning models in a more fine-grained way. So the challenge is how to identify them to avoid unnecessary cleaning operations, because data cleaning is always expensive because it always needs humans' help. So we first use a table to overview this. So here, the clean ML is a benchmark for joint data cleaning for machine learning. It tests the impacts of these data errors on 7 typical machine learning methods like multi-regression, decision tree, and random forest, so on and so forth. To summarize, we draw a table to illustrate the relationships between data errors and the machine learning performance. So the column positive means that whether the cleaning contain errors has a positive effect on the model. And the negative column denotes that whether the cleaning operations has a negative effect on the model. And the model selection denotes that whether the model selection can promote the positive or eliminate the negative effects. And we can from the table that the first row indicates that the second row indicates that the cleaning duplicates will degrade the model performance because the data distribution may be changed. But the degradation can be eliminated by judiciously selecting models. So for another example, cleaning the outliers may have positive or negative impacts on the machine learning tasks, which highly depends on the specific machine learning task or data size. So what's more, making the data more consistent is not likely to influence the model, but the model selection increases the probability of having positive impacts. And verifying mislabels and imputing missing values have positive impacts on the machine learning tasks. So let's see whether cleaning certain items have impact on the machine models. Then let's see a concrete method about data cleaning for machine learning. First, the active clean. It first justify whether we need to clean the data to obtain a well-performed model. So from figure E, so this cross denotes the dirty data. There are 5 data objects, and the green ones are the clean version of this cross. So we can see that we train 2 models, they are so different. So this figure shows that the cleaning is necessary for the machine learning task. And the second figure answers the question that whether we can just clean a part of data and then train a model. So the answer is not. So for example, if we just clean the 4th and 5th data object, and we can see that the red line and the blue line are still very different, and they are so the model cannot perform well at the blue line, the blue model. So we cannot do not clean, but we also cannot just clean a part of data. So then whether we can just clean a part of data and produce a high quality label, the answer is yes. So at a high level, the reason why the dirty data degrades the performance is that they mislead the gradient computation. Then if one can clean part of dirty data, compute the variations of the gradients and estimate the gradients of the uncleaned data. And they can quickly converge with a small number of clean data. So active clean consists of 4 models, which are sampler, cleaner, updater, and estimator respectively. The sampler is utilized to select a batch of records to be cleaned, where the selection criterion is measured by how much improvement can be made after cleaning a record. That is the variation of the gradient. The improvement is computed by the estimator based on the current cleaned data. Then the selected record will be checked and repaired by the cleaning, which can be conducted by humans. Next, the updater updates the gradient of the entire dataset based on the verified dirty data. And these 4 steps iterate until the budget is used up. So there is another work called boost clean. which aims to clean the data where an attribute is out of range. It takes as input a dataset a set of predefined functions for detecting and repairing out-of-range values, as well as a black box model. These values will definitely degrade the model performance. So the optimization goal of the boost clean is to explore the best sequence of the repair operation so as to best improve the model. Rather than constantly enumerating every record in the original dataset and clean it, it makes the observation that detecting errors and applying a cleaning function on a dataset can be seen as generate a set of new features, and then a new model can be trained on the cleaned dataset. So they use the boosting idea, which views each repair operation as a weak classifier and combine many of them collectively to make predictions. To be specific, in each training iteration, it first generates the best classifier on current dataset and weighs the dataset considering the mispredictions by current classifiers and repeats the above step until the budget is used up. So the CP clean focus on the reasoning about the impact of missing values on downstream machine learning tasks. We suppose a dataset has n missing values and the domain set is m. We have m exponential n possible imputations. So all the imputations consists of a possible word, and each of them corresponds to a model. We hope that the predicate label of all models are relatively consistent for each tuple, so that the less cleaning operations are necessary. So an ideal case is that all labels are the same for an example. And this example is called the certain prediction. Intuitively, if all test examples are certain predicates, it is wasteful to impute the missing values. Therefore, the optimization goal of CP clean is to prioritize imputing the record that are likely to make the test examples have consistent labels. That is supposed to be certain predictions. So a straightforward method is to train all the models and make predictions, which is too expensive because training is inefficient and the possible world is extremely large. So CP clean addresses this problem by restricting the models to KNN classifier in this way. To compute whether an example is certain practice, we only need to consider the similarity score between the example and the training data rather than training the models. Then the DA GAN also focuses on the difference of the distribution of missing values on multiple attributes between training data and test data. This often causes the performance degradation on test data, and it is a common scenario because a single trained model is likely to be used in different test cases with different missing value distributions. To address it, the basic idea of DA GAN is to reduce the divergence data distribution between training data and the test data. The key idea is to capture the missing value distribution from the test data using GAN, and it adapts the training data to capture the distribution without changing the labels. After that, it refines the machine learning model by retraining with adapted data. So here is a comparison of data cleaning, and the first column is method, and all of them focus on improve the model, and they use different method, and some of them are automatic and some are not because they need human, and they clean misvalues, outliers, some of them, and they follow different model types. So the pros of these methods are that the data cleaning for machine learning, considering both both the data and machine learning algorithm. And these methods save much cleaning costs because large volume of unnecessary operations are saved. And the cons are that the data cleaning always needs much human effort. And the existing method always refer to error types like just outliers or missing values. And some of them also restrict to the machine learning models like convex models. So here is the takeaway. So data cleaning aims to detect, repair data errors, but not all the cleaning operations can directly improve the machine learning models. And some may even have bad impact, like the duplicates. So cleaning directly for machine learning always focuses on looking into the machine learning algorithm and finding the close relationships between data and the algorithms. So it's very interesting and important. Then let's talk about the data labeling. So we categorize the data labeling into three groups. One is crowdsourcing. It leverages the crowd intelligence to label the data. And the second one is active cleaning, which hires high quality experts to label. And the final one is weak supervision, which leverages the rules and imperfect labels to directly train the model. So here is the comparisons of different data labeling methods. So we compare them through the data label quality, label cost, and label latency, and whether it is for the machine learning. So the crowdsourcing leverages the human intelligence to install the tasks that hard for the computer, like labeling in the machine learning. So it consists of the three parts. So the requester submit tasks, and the crowdsourcing platform like Amazon Mechanical Turk publish the tasks, and the workers find interest tasks, return answers, and the requester collects the answers. So the challenges in the crowdsourcing are threefold, and they have trade-off. First, the cost. The crowd is not free, so we should reduce the monetary cost by some pruning techniques and some deductive strategies. And the second one is the quality and the crowd, because crowd may return incorrect answers because there may be some low quality workers. And the third one is the latency, because the crowd is not real time. So there exists trade-off between these three factors. So for example, if you want to improve quality, you may assign your task to multiple workers, and so the cost is large. So the pros of the crowdsourcing method is that a large number of intelligent workers you can hire. So thanks for the crowdsourcing platforms like AMT, we can hire workers very easily. So the disadvantage are that crowd workers are error prone, so you need to improve quality. And crowd workers are not free, and this method is not directly for the downstream models. It just generates the labels, and then you aggregate their answers and inference the final labels, and then you use these labels to train the model. So it's not direct. And the second one is active learning. So it is a widely studied work, and there are many tutorials and surveys you can refer to. So we just generally say something about this. So first is uncertainty sampling. It's very simple. We just use entropy to measure the uncertainty. And the second one is query by community. So the basic idea is similar to the previous one. It's just you can just test multiple models and use the uncertainty of the multiple models to select the data objects you need to label. And and then following the expected model change, it selects example that would introduce the greatest change to the current model. So the change is measured by the gradient. So and the last one is similar to the third one. It measures the generation level is likely to be reduced of a certain example and choose the example that can reduce the generalization error most. So the pros of the active learning are that experts are always high quality, and it is directly for downstream models because in each iteration, the active learning checks the relationship between data and models. And the disadvantage are that experts are always very expensive, and and it needs high latency to label this data. Then we come to the weak supervision. So the first part is learning from imperfect labels. So for cross-sourcing, it also generates many imperfect labels, but you have to so given one object, you ask five workers to label this, and then you get five answers, and you infer based on that. But so the the learning from imperfect labels, so this method is just train from these imperfect labels. The given observed training data D, and they directly estimate the weight factor, estimate the quality of the worker, and infer the classification of each instance. So they can use the EM algorithm to conduct this. So then the other one is data programming. So many machine learning applications need a large number of training data, which is very expensive to obtain, even resulting to the crowd workers. So data programming techniques have been proposed to generate a large number of weak labels using multiple labeling functions rather than labeling for each example. So where each function can be written by humans. Naturally, a single function is far from generating high-quality labels, so multiple functions should be combined to generate labels. So the most straightforward method of combination is majority voting, but it does not consider the correlations and qualities of different functions. So to address this, the Snorkel is proposed to aggregate the results of multiple labeling functions to infer the final labels. So with specific Snorkel, first provides a user-friendly interface and ask the experts to provide the high-quality rules. The labeling function, applying this function to data gives a labeling matrix L, and and then use this rules to build a fact graph. So L denotes the labeling function, and N denotes the new labels, and they use a graph model to deduce the final labels. So that's a general framework of the data programming. So given some unlevel data and some weak supervision sources like human provided rules, and we generate a label matrix and use a fact graph to build a model on these rules, model their relationships, and then they build a deep neural networks to directly use these labels to train a classifier. So the advantage of weak supervision is that it achieves both low cost and high quality due to the rules and models built on the rules, and it directly follows the downstream models. And the disadvantage is that the rules should be carefully designed by experts. So if the many rules are not being trained, so the quality is horrible. And the second one is that more theoretical guarantees should be provided for the weak supervision. And so the takeaway of the labeling, data labeling, so the data labeling always introduces trade-off between quality, cost, and the latency. So the one of typical labeling method is crowdsourcing, which is cheap but low quality, and the active learning is expensive but high quality. So recently, weak supervision is a good choice for achieving high quality but with low cost, and it is directly for downstream machine learning. Then let's talk about the in-ML field top of the feature selection. So let's see the comparison of feature selection. There are two main goals. First is for model quality, and the second one is for model efficiency. And the first one is always conducted by machine learning community, and the second one that we focus on is done by DB community. So since the model efficiency does not influence the model quality, so we just care about the efficiency in the second part. So So first, let's briefly talk about the feature selection methods in machine learning community. So uh, totally we divide it into three parts. So the first is filter-based method. It separates the feature selection from the learning algorithms. So we do not need to train anymore in the feature selection strategy, in the feature selection process. So the second one is wrapper-based method. It considers the predictive accuracy on select feature subsets. So the main idea is to enumerate many subsets and select the best ones by continuous training. And the third one is embedded-based method. It embeds the feature selection into the machine learning model, like the tree model, or GPT, or the deep learning model. So in general, the DB-based techniques can be used to accelerate feature selection. So we mainly focus on the wrapper-based method for acceleration. So the first technique is batching. So the wrapper-based method is defined as follows. So given a set of features, so we aim to select the optimal subset that achieve the best performance. So the challenge is that there are a number of possible subsets have to be tested and loaded many times, which incurs much I/O cost. So the key idea to solve that is to batch some subsets together and evaluate them in one table scale. So given the problem is as follows. So given a memory constraint S, so each subset Fi has a memory constraint. I have a memory requirement Mf for training. For example, the subset F1 may have a memory requirement M1 and F2 has a requirement F2. So different subset have different requirements. So totally we have a memory constraint S and we aim to batch some subset together and evaluate them in one table scale. So the optimization goal is to minimize the number of table scale, which is the NP hard problem. So even if we have batch technique, we have another challenge is that we have to load each batch via table scan and then evaluate, which is still example. So we can use materialization technique to materialize some batches of tables to reduce the read cost. So the key motivation is that each batch has different frequency to be loaded. So the problem is to select an optimal materialized solution where MI is a materialized batch. So this considers the materialized cost of the batch and the I/O saving of the batch. So this is trade-off. So we can also see this problem as a machine learning pipeline. So each machine learning pipeline can be regarded as a DHE graph. It starts from loading the data and conduct feature engineering for each attribute, which includes the extract the feature, so make the feature into bucket and so on and so forth, many operations. And in the typical machine learning pipeline, we have to do this in iterations because we have to we have to add features, delete features, and tune the hyperparameters. So the intermediate result can be materialized to, for example, we can materialize the each bucket as these results, and so in the next iteration we do not have to rebuild this pipeline. So it is also it can be also solved by a materialization idea. So it considers the rebuild cost and the materialized cost. This is a trade-off. So the other method is active learning. Use active learning to do feature selection. So the challenge is that the model training, the convergence takes time. So it clusters the data items in the training set and uses active learning based method to select the high utility data for training. We can see from the graph, from the figure that this method converges very early than the baseline. Next, we talk about the model selection. So model selection aims to select the optimal model structures or hyperparameters. So the goal is to improve the model performance and the model selection efficiency. So let's first talk about briefly the model selection method in the machine learning community. So it consists of two directions. One is the traditional model selection, which selects from traditional models like SVM, random forest, KNN, so on and so forth. And the other one is the neural architecture search in AIs. This is for deep learning model, including the model structures and hyperparameter settings. So the DB-based parallel techniques can be used to accelerate the model selection, and that's our focus in this tutorial. So here's the comparisons of in parallel model selection method. So there are different methods, and they care about different optimization goals. So first, we care about the high throughput that means so we can test how many we can test how many model configurations in parallel, and then we care about the high scalability and how much distance we can test. And then we want to ensure the good convergence. And then we want to guarantee a good reproducibility. We want that the first running of the model selection and the result is the same as the second one and third. So the first is the task parallel. So the challenge is that the model selection needs high throughput. So current machine learning system focus on training one model at a time. So this method tests different training configurations on different workers in parallel. So the key idea is they copy their data to multiple workers and run different configurations in parallel. So the drawback is apparently it's needs high storage cost, so the scalability is low. So that another challenge appears is the high scalability. So the BSP addresses this challenge by partitioning the dataset across workers and train one model in parallel on multiple data partitions, and they average the model parameters and achieve the final models. But the drawback, however, it has poor convergence. So to address this convergence challenge, so the parameter server is proposed. It can be taken as a fine-grained way of BSP, which also runs each configuration in parallel. The difference is that the worker nodes send the updated gradients when each mini batch is finished and then pull the latest model from the master node. So there are two classes of the parameter servers, synchronous and asynchronous. And the former one asks the master to compute the average updated gradient when all workers finish a mini-match. So the latter one asks the master to train whenever an update occurs. Therefore, the asynchronous parameter server has a good scalability but poor reproducibility. Besides, the synchronous parameter server has better convergence because of the fresh gradient updates, but higher overhead due to the synchronization. Compared with the BSP, overall parameter server has higher scalability and better convergence because of its finer granularity in mini batch. But the communication cost is higher due to the frequent communication. So to achieve high communication efficiency, so the model hop parallel technique is proposed. It combines the idea of task parallel and BSP to run configurations in parallel on both task and data level. So they remove the master node and they conduct the model hop between each partition. And given a data set, a set of model configuration to be executed, It first shuffles and partitions data set, and different partition will be distributed to different worker nodes. And since there are multiple worker nodes, so this method evaluates the multiple configurations in parallel. So in each training epoch, it selects P models from S to train using the SGD and different partitions. After that, each model will hop to the next work node in accordance to the pre-generated hop schedule. So after several hops, all the model will be trained over the entire data set. So let's see the takeaway of the feature selection and the model selection. They are both hot topics in machine learning studied for years, which influence the model performance a lot. And then fortunately, they can be accelerated using the DB-based techniques like batching, materialization, and parallelism. So the above method accelerate the feature selection and model selection stages without trading off the model. Then let's talk about how to accelerate the training phase while computing the loss and the inference stage. So we talk about this topic from four aspects, from the low level to high level. The first is the expression level, which uses the linear algebra optimization to accelerate the loss or gradient computation. And the second one is the table level. So it is called the factorized IML. This because the machine learning algorithm always involve multiple tables, and they need to join, and join is always inefficient. And the third one is the computation graph level optimization, which optimizes the computation graph in the deep learning. And the last one is hardware acceleration. So let's first look at the linear algebra optimization. So the motivation is that most machine learning algorithms relies on the linear algebra. So rewriting a linear algebra expressions can greatly reduce the execution time. So we categorize this topic into three parts. First one is in database linear algebra optimization. So this work is proposed to execute the linear algebra operation into the base so that the computation of these operations are likely to be accelerated because the data storage and the computation will be managed by the database systems. So the time of data transformation can be saved, and some database techniques like index join can be utilized for efficiency. So to this end, this work uses sparse representation to represent the matrix. And then this method works well for the sparse matrix, but it's not good for dense matrix because it incurs much storage overhead, and it cannot be highly optimized linear algebra libraries like BRAS. And to address this, so the UD user-defined function is proposed to compute the dot product of two vectors. It works fine for dense matrices. So for example, if we want to fit a simple model, we can just do it in database, but it just work well for the simple model, and some linear algebra optimization cannot be used because it is executed in the database. So the process saves the data transfer cost, and some database optimization can be utilized. But the costs are they just support simple machine learning algorithm and cannot support hardware like GPU and FPGA, and it negates the optimization of linear algebra in the machine learning algorithm. So let's see how to optimize the linear algebra expression. First is the rule-based optimization. It reduces the unnecessary intermediate results. For example, it transfers the x transpose y to y transpose x and transpose. So it passes the LA expressions to a DAG of operators and rewrite with some rules. And if some matrix size is too large, we can use the distributed computation, and we can dynamically recomputing for input matrix at runtime. But it is a rule-based method, so it needs heavy development efforts. So if the machine learning expression change a little, so the pattern can be recognized by the rules. So the spoof is proposed. The key idea is to transfer LA to the relational algebra, and then use the typical relational algebra optimization rewriting techniques to rewrite the relational algebra and then transfer it back to the linear algebra. So the many relational algebra optimization like drawing and aggregate can be utilized. And then that work, the spoof can now search through the whole space of the equivalent LA expression. So the spoof is proposed to provide 7 rules for RA optimization. They prove that the rules are complete, and they use the equality situation to explore the rule space of the RA optimization. So the prompts are that the acceleration in a very fine-grained way, considering the machine learning expressions. And the other advantage is that the other acceleration techniques can also be utilized. And the disadvantage is that it do not consider the optimization potential of the machine learning task where multiple tables are involved. So let's talk about the factorized machine learning. It considers the multi-tables, how to join them, how to run the machine learning algorithm without joining the tables. So in machine learning community, people always assume that input data are stored in a single table. However, the enterprise data are always scattered in multiple relational tables due to normalization. So data analysis must materialize data in a single table by drawing all the tables and export the data out of databases. This causes large computational cost and storage overhead, as well as data leakage risk. So factorized ML is proposed to address these issues by supporting machine learning on multiple relation tables and pushing the machine learning operators down to each single table. For example, we see that if we want to join the table S and R and to run a simple machine learning algorithm like the W transpose and multiply the X, and we can see that if we push down the W multiply S to each single table, we can save many computation operation. And also factorized the method can reduce the redundancy of computation compared to the traditional computer after drawing ways. They are difficult to be applied as they need a complete implementation of machine learning algorithm, which takes too much effort. To address this, so the researchers develop a framework that aims to support a number of machine learning algorithms with few modifications efficiently. To this end, it defines a new data type called normalized matrix, connects the high-level machine learning algorithms and the low-level matrix computation operators. Then most all machine learning algorithm built on basic matrix operations can be implemented by the normalized matrix. So with this matrix K, the normalization information from origin data can be preserved, and the basic matrix operations such as matrix multiplication and cross product and matrix inversion can be implemented with pushdown. And furthermore, the learning task always needs a batch of join queries followed by aggregation. So the similar idea is always applied to push aggregations operator down to draw to tables, reduce the size of intermediate results, saving the joint cost. So queries in a batch can share the computation. So then let's talk about a more high-level optimization is computation graph optimization. So in this part, many typical deep neural network architectures have become larger and deeper, resulting in a large number of computation resources. To solve this, it's natural to optimize computations in a CNN, which is defined as a computation graph of mathematical operators. So existing deep learning framework like TensorFlow and PyTorch optimize an input graph by performing greedy rule-based substitution on it. Each substitution replaces a subgraph matching a specific pattern with a new subgraph that is equivalent to the original one. For example, operator fusion integrates multiple operations into a single one, which removes the intermediate results. So the main challenge of the computation graph is that the search space of all equivalent computation graph is exponentially large, which brings huge costs and requires higher search efficiency. So existing deep learning systems solve this problem using a rule-based method that continuously improves the efficiency, but they may get stuck in the local optima. To solve the problem, so the method flow is proposed to establish a cost model to efficiently estimate the time usage of computing network considering the rules with respect to the statistics like flaws, memory usage, and number of kernel launches, and so on and so forth. Unlike PyTorch, MetaFlow considers the rules with increasing cost in the intermediate computation graph to seek more optimization opportunities. For example, as shown in the figure, enlarged substitution is first applied to enlarge a convolutional layer, which in fact increases the intermediate total cost. However, after the subsequent substitutions that fuse operations like add and reload together, the final optimized computation graph can achieve a higher speed up. So the backtracking search over the relaxed substitution rules is applied to accelerate the computation graph processing. So to thoroughly optimize this problem, so researchers formally define it as a cost minimization problem, specifically taking as input an initial computation graph G, a set of substitution rules, the substitution length limit K, and a cost function. The optimizing computation graph problem is to find a graph substitution sequence P with length no more than K, such that the cost is minimized. The problem is proven to be NP-hard and efficient heuristic method with a polynomial time complexity is proposed for more practical usage. So hardwares are always utilized to accelerate the machine learning algorithm like GPU. Recently, many researchers have studied how to use specialized hardware design to accelerate the in-database execution of complicated data analytics. So the DANA is a work about the integration of FPGA and DBMS. So the challenge is manually leverage FPGA is tedious and we need to write the FPGA code. So and also the direct combining the FPGA and DBMS leads to inefficiency because of the limitation of the bandwidth of the GPU. So to address these, the key ideas are firstly to automatically translate the UDF for execution on FPGA. We can use a Python package to encapsulate the FPGA code. And to address the second challenge, they bypass GPU and its memory directly communicating with the RDMS buffer pool to saturate the FPGA bandwidth. And the second method is to integrate the column store DBMS with machine learning over FPGA to get high data analytic efficiency. So the challenges are, so in the column store DBMS, the SED algorithm is always adopted, but it is poor in cache located, thereby inefficient. And the second challenge is that for the column store, we also need to compress and encrypt the data, so the efficiency is low. So the key idea is to leverage the FPGA to accelerate the SCD and the data compression using this parallelism ability. And the third one is about the GPU. So the motivation is that the transfer between CPU and GPU needs to go through the small bandwidth PCLU. So the solution is to purely use GPU for analysis without considering CPU. But this arises two challenges. One is the synchronization because between a large number of threads of GPU is very inefficient. And the second one is each thread is very weak in terms of the memory and the computation ability. So the key idea is to treat the thread block as a basic execution unit. And each thread block can process a tail of items, and it can improve the memory and computation ability. So the takeaway is that the training and inference steps can be accelerated using many DB-based techniques like linear algebra, factorized ML, and computation graph optimization. They accelerate mainly by optimizing the gradient computation across one or multiple tables, and the acceleration does not influence the model accuracy.
Now let's come to the final part, the post-ML. Is the model management. So after deploy the model, we may have a large number of models to be managed. We should store them and query them. And then we come to the model deployment. And then the model should serve to the users. And at this time, we can debug the models, the machine learning pipeline based on the user's complaints. So first, let's see the model storage and query. So what data should be stored? So that it's model relevant data like parameters, gradient, information logs, and the training test data. So the key point is it's a model storage framework should be compatible to multiple machine learning frameworks, and the users can easily track the model, and there will be a user-friendly interface. And let's see, the ModelDB, it provides native client libraries that support different machine learning environments, and it has backend to store model and front-end to interact with users. And then the Model Hub manages deep learning large-scale artifacts. It can try different architectures and features and store many hyperparameters for fine-tuning. And it also provides gate-based model versioning and cyclic query for deriving new models. And it can publish, discover, and use models. So it can the Model Hub can list models, describe models, and compare models and evaluate the model. And it can also select the models and construct new models by mutating existing models and try new techniques. And then we come to the model diagnosis. So while the model development, there may be some failures. So we should know why does the model fail? Because of data or because of the model? So there may be some questions like which input pixels are the most important and how does the neurons work? So from the view of database, so there'll be a large number of parameters, vectors. So the model diagnose needs to uh, check many parameters, which results in large storage cost and high computational cost. So our goal is to reduce the storage cost to speed up the diagnose query and easy to use interface. So Mistake can efficiently store and query model intermediates for model diagnose. It supports both traditional ML and the DL model. So it can query the learned parameters, log file, gradients, and so on and so forth. So to reduce the storage cost, it uses the quantization technique and remove the duplicates parameters. And it also provides a materialization technique that considering the trade-off between rerun the entire pipeline or save the model intermediates between the different iterations of the machine learning pipeline. Is a trade-off between storage cost and the query time. And there is also a sampling method for deep learning model diagnosis. It is to accelerate the execution of model diagnosis query by producing approximate yet acceptable results. It focuses on the representation in the latent space because vectors there can reduce the dimensionality of the data and it will be more efficient. And it also focuses on the decision boundary in the latent space because there may be many important vectors to check the outliers. And then after the model deployment, we come to the deployment and serving. So the model deployment is to deploy the model to production in order to serve for prediction. And the model serving is to support low latency and high throughput model prediction. And the goal is to guarantee low latency and high throughput and easy to use API. And the Clipper provides a low latency online prediction service system which decouples the application and models. And there is a model selection layers to improve the accuracy and a model abstraction layer to provide a user-friendly interface and bounding the latency and the throughput. And then we come to the machine learning pipeline that debugging. It is the debugging after the development stage, unlike the model diagnosis. It can also detect the data errors and model bugs. So RAIN is a typical system for machine learning pipeline debugging. So there may be some data errors lead to the output errors through the trained models, label prediction, and workflow. So what we need to do is to based on the user find errors and to detect the reversely detect the errors in the input data. So the RAIN proposed a query 2.0. This is a cycle plus the machine learning predicates. So based on that, the users can complain about some incorrect results, and the RAIN can use something like the inference function to identify the bugging issues on the training data. So what does the influence function mean? It is to identify the weak data. It may be weak labels or outliers or dirty data, which has a large impact on the model performance without training the model. So it is very efficient. So the RAIN is to leverage the influence function to identify the minimum set of training records and can solve the user's complaint by removing this bad data points in the training data. So here's the takeaway. So model manager always needs user-friendly interface to interact, and it should handle cross-platform nodes of machine learning and model debugging when they figures out failures causes in data or models.
Okay, finally, we will introduce some challenges and some open problems. So the first, I will introduce some open problem of AI4DB. So I think most important is to design lightweight model training method. For example, for norm tuning and for some index recommendation, it may take a lot of time for training, and especially for cold start. So can we design a lightweight model training? And it's important, and it's very important to utilize the training for different components. Or can we have some encoding methods that support knob tuning and some index advisor recommendation? So there are some challenges, for example, factorization. Can we have a model that can be utilized to support different scenarios? And can we extract effective features? And the data collection, how can we collect training data, for example, from the production machine? So it's very important to guarantee the performance of the running queries. But how can we collect data that not affect the performance of the production machines? And model testing. So how can we test model, whether the model can be used and applied to the real scenarios? So we think that very important to design some, for example, future learning and some data-driven to knowledge-driven. For example, can we use knowledge to help us to automate database? And the next one is high adaptability. For example, can we adapt the method to different workloads? For example, different query operators and different plan structures. Adapt to different data sets, different database instances, and different database systems. So we may use some meta learning and transfer learning technique to transfer one scenario to another scenario. I think this is very important. You know that training database can support lots of scenarios, and usually they can guarantee we get good results for each scenario. But for machine learning, how can we guarantee that we can get good performance for each scenario? I think this is very important. And the next one is model validation. I think this is also very important. For example, whether model is effective, can we apply or deploy this model? And whether a model can outperform existing method, for example, existing database. So we need to model verification and whether a model can adapt to different scenarios. I think that they require such model validation techniques. And you know that there are lots of learning-based database design. So can we to design some database assembly techniques? For example, you know there are more than 400 databases in the world. Why we have such large number of databases? Because each database wants to support different scenarios. So we have some KV graph and lots of databases. But you know that the techniques are limited. For example, we only have this techniques. Can we to design the techniques and then we can automatically assemble this technique to support different applications? I think this is rather important. So how can we automatically assemble the different components to design to support different scenarios? And most of existing techniques work on some or AP queries. So you know that for these queries usually read only. We won't affect the data generation and the data update. But for RITP and HTTP, I think are very important to meet the performance requirements and to guarantee the data integrity. So how to achieve the SRA agreement and how to adapt to different workloads and how to support different query optimization. So there are some challenges, for example, data update, schema update, and some concurrency, and some log complex, and some trained chains. So how to support this? I think this is very important to support the transactions on database. And next, I will introduce some open problem for DB4AI. The first pre-machine learning. So I think the data discovery, especially the item level database discovery, is very important. You know that when a model on data sets is not good on testing data, so what's the reason? The model is not good or the data is not good. I think this is a very, very important problem. So usually can we to find that if data is not good, can we automatically discover the data from data lake? So here is some item level based data discovery. For example, we discover some data tuples, or discuss some pictures, some images, or discuss some videos. So how can we to achieve this? For example, can we to discover more data to improve the model and to make the model better and can deploy on the applications? I think this is very important. And this is usually model aware discovery. So for this model, we can discuss all the data. Usually, the traditional data discovery focus on some database application, do not touch the machine learning techniques. And second one is the deep learning, cleaning for the deep learning. So you know that we have some data cleaning techniques. So for example, the missing data, some outlier. But for deep learning models, for machine learning models, whether the cleaning data cleaning is very important. So whether we want to clean the data, whether we clean data can improve the model quality, I think this is rather important. So there are some model aware data cleaning techniques. Next one is in machine learning. So can we build a machine learning optimizer? For example, we design machine learning operators, machine learning cost model, and machine learning optimization. So there are lots of work on using some database techniques, including database rewriting, database optimizer to work on the machine learning to make machine learning run much faster and much powerful. And there are also some work on hybrid database and machine learning optimizer. For example, in training database, we usually support some Scala operation, but in machine learning, we support some tensor. So can we combine them together? For example, a SQL query including both some database operation and some machine learning operations. So can we optimize the SQL queries? I think this is rather important. This is maybe extend the traditional relational algebra to have some new algebra to support some machine learning and database. I think this open problem and there call for arms from both database theory and database optimization people to work on this. And the next one is we have lots of machine models. So can we utilize models to design new models? This is just like some views. For example, we have some tables, we can create views, use the views to automate some queries. Here we have lots of models. Can we decompose the model and recompose the model to construct some new models to support some new application? I think yes, there's a lot of scenarios we need to study. For example, in current works, they rely on some machine learning developer. For example, some machine learning developer, so given a new scenario, they will try different model, try different data, and tune the parameter, and they need manually to do this. And then if the models become better, they will continue to tune the model. And if not, they will think about how to improve the model. So this is usually a human intensive work. So can we utilize some new automatic techniques to automatically to decompose the model and recompose the model? I think this is very similar to view-based techniques. I think there are lots of opportunities. Okay, this all tutorials. Thank you for coming, and we are open for some questions to discuss some recent works and the progress for DB4AI and AI4DB. Thank you so much for your attention.